welcome everyone. So as I introduced myself, I'm Kevin Hughes, and this is a course on some topics in the circle method. So starting with the Waring's problem, and then moving into more modern developments in discrete harmonic analysis or arithmetic harmonic analysis. So there will be three topics, really. An introduction to the circle method, because we're going to be using that throughout. And in particular, Waring's problem, which for me is a big motivating problem. While we, and then we'll move on to the discrete spherical averages and their maximal functions. So that's one of these more modern variants on Waring's problem that we're going to look into, and we'll spend a bit of time there going over sort of the seminal results. And then we'll move on to discrete restriction theory, which is also another huge topic in this area. And with luck and time, we'll be able to get to some of the recent developments there in terms of the Vinograd mean value theorems, and maybe highlight a couple of the techniques that go into that. But we'll start with some fundamentals there and some classical results. So let me see. I don't see myself on here. Does anyone? Okay.
I see you. Is that okay?
Yeah.
Okay. Yeah, it's just on my computer, or sorry, on my phone I wasn't seeing. But okay, cool. I'll keep going. Right, so Waring's problem. Waring's problem is actually a really old problem. It's like 350 years old now. And it was really just a hypothesis that Edward Waring, who was somewhere in England, Oxford or Cambridge, presumably, asserted that you can write every natural number as either the sum of 4 squares or 9 cubes, 19 biquadrats, which is the old term for fourth powers, and so on. When he wrote this letter, and so on usually means that if you give me some degree k, like 10, I look at all the 10th powers, you can find some number of 10th powers that you can represent all natural numbers as. And when you do this, you're actually allowing to have 0, right? So you can have, for instance, 7 is 1 squared plus 1 squared plus 1 squared plus 2 squared, right? And 6 would be 0 squared plus 1 squared plus 1 squared plus 2 squared. So I allow 0 to be this buffer. You don't have to make it all positive integers. Okay. And this problem, as stated in this sort of form that you can solve for every integer, was actually proved by Hilbert at the beginning of the 20th century. And so he gave this statement, and he'd agree. You can find that there's some number of powers, so you can represent every number. But the powers to get that, like the number of variables d, depending on your power k, grew immensely fast. So it was something like a tower exponential. It was very poor balance. Luckily, so something that's much further from the truth, like sums of 4 squares and sums of 9 cubes and so on. Luckily, Hardy and Littlewood consider this a bit more. And they actually asked how many ways you can represent each number as a sum of 4 squares or 5 squares or so on, or 9 cubes, or 106 powers, and so on. And in doing so, Hilbert's methods were very algebraic. It was very much manipulating equations and using some invariant theory, and very sort of hands-on and gritty, but it worked. And it didn't really use much or any analysis. Instead, Hardy and Littlewood took a very analytic approach, and they introduced something called the circle method, which had some vestiges in previous work with Hardy Ramanujan. Okay, and then so that was introduced in about 1920, and for the past 100 years, it's sort of been a mainstay of analytic number theory. We're still quite far from getting the optimal solution to Waring's problem, though a lot more is known than when Hardy and Littlewood started on this. And in particular, there's been some fantastic progress on the Vinograd mean value conjectures, or the optimal estimates in the Vinograd mean value theorems, several different names for it, that were only solved 5 years ago by Bourgain, Demeter, Guth, and by Woolley. Okay. But nowadays, we're going to study Waring's problem in the sort of modern form. And that's where you're going to ask for the asymptotics and the number of ways to write a number as a sum of 4 squares or 9 cubes or so on. Okay. So their result was roughly the following. If I take some degree k, and I want to tell myself, what's the number of ways I can write an integer n as a sum of kth powers as a sum of d kth powers, that is d variables, then you have the following asymptotic. And this asymptotic holds as soon as I have enough variables, okay? And of course, this is going to be in degrees greater than or equal to 2. I can write every integer as a sum of 1/1th power, namely itself. So the problem isn't so interesting in that regard, though there are interesting variants to consider, such as the Goldbach problem. So what they proved was, if I look at those number of representations, number way to write n as a sum of d kth powers, then it turns out you have an asymptotic formula for it. So momentarily ignoring this auxiliary term, you see that the main term is going to grow like n to the d over k minus 1, where d was the number of variables and k was the degree, right? Up to some other factors, this factor here is the volume of some unit surface. And these other factors are going to be the p-adic densities for the solutions to this equation. Right, but that's of course all up to some error term. You don't actually get equality except very rarely. And this error term, well, you really just want to show that it's little o, meaning that it's just barely smaller than the preceding term. And what often happens is that you actually save some little power right here. So you get some that it's like n to the minus delta for some positive delta. And that delta will depend on the degree, the dimension d, but it will not depend on n, of course, right? And then there's some implicit constant here that depends on everything in sight except for n. All right. Are there any questions on what this is so far? All right, great. What is the p-adic density? So this term here in the middle is a real density. It's measuring what this surface looks like. This hypersurface is measuring the d minus 1 dimensional volume of this hypersurface. Now these p-adic densities are doing the same thing, but in the p-adics. So not over R, but over QP. Okay. And we'll get to precisely what that means as we go on, probably in the third lecture or so. Great. So the way they did this was they introduced the circle method, right? So again, this built on Hardy and Ramanujan's work regarding partitions. And this is really the method that underlies a lot of these problems, okay? It really goes back to a certain orthogonality relation. You're gonna write a function in terms of an oscillatory integral. For us, that particular function is a delta function. So delta naught of n is 1 if n equals 0, and it's 0 otherwise. Right, so if we're not, oh, that should be a little n. All right, we're gonna make it a big n. Okay. And you can just check from calculus that this identity right here in the middle is true. Now doing that, you can rewrite a counting function such as this, where I'm counting the number of points out, the number of representations of my integer as an oscillatory integral that involves an exponential sum. Okay. And that right there is the catalyst for what Hardy and Ramanujan do. Okay. And you can already see that you're bringing in Fourier analysis into play, right? As soon as you write something as an oscillatory integral and you decide you're going to study the object from that point of view, you've really made a Fourier analytic choice. Okay. Now we're not going to study this directly at the moment, but we'll get on to sort of what it is we want to do. Great. So our first goal is to prove this Hardy-Littlewood theorem, that the number of representations is asymptotically, what was it? Some constant, depending on n, times some factor, times n to the d over k minus 1. This asymptotic just means there's some lower order term that, that is smaller than this right-hand term, okay? And in the course, I'll actually prove it for sums of 5 or more squares and outline how to do it in higher degrees. We'll find that, you know, if you could give a whole course on just the circle method doing these things, and we don't have that much time. But as we do it, you know, I'll be introducing a lot of things like, okay, we've already seen this delta method representation, but we'll also use Poisson summation, Bial's inequality, stationary phase, p-adic singular integrals, and so on. But I will try to phrase things as harmonic analytic as I can, because that's, or at least as much as I'm comfortable with. And so for instance, like just the use of the word p-adic singular integral is already something that isn't used very much by analytic number theorists. Okay, but this is going to be a blend of number theory and analysis. All right. So here's a couple extra slides just in case anyone had some questions that I should make some comments on. Give a moment. Okay. So once we have an understanding of these asymptotics and roughly how many ways there are to represent a number, we can start moving to a more geometric question, right? And when that geometric question is predicated on the following other revolutionary result. So the circle method started a whole independent program in analytic number theory that's been well developed by lots of people. And similarly, Hardy and Littlewood introduced something else called the maximal function, or the Hardy-Littlewood maximal function. And this also revolutionized harmonic analysis. It underpins, it's one of the first things you learn in a graduate course in harmonic analysis, and it sort of underpins a lot of future study. It's kind of the best operator in many ways. And it's the one that if you can reduce your problem down to that operator, you understand it very well, right? Sort of it's the prototypical operator in many ways. And so how is this defined? Well, basically I take some nice function, say it's continuous, or it could be Schwartz, however nice you want it to be, on RD, so d-dimensional Euclidean space, and I define the ball average of radius r by this formula. So at each point x, I look at all the values of f of x, or I should say f of x plus y, so all the values inside that ball, and I take the average over that ball. Okay, this gives me some nice average. And the maximal function is just defined as at each point, defined as the supremum of all those averages. Okay. This may seem like a strange thing to do, and stranger still, perhaps, is the following bound for it. We have that the maximal function is bounded on LP of RD for all p greater than 1. And it's also weak type 1, 1. Moreover, these bounds are sharp, up to some implied constants I haven't recorded, meaning that I don't have a bound from L1 to L1. In fact, you never do whenever your function is non-trivial. So just for those who don't work with LP spaces every day, recall that the LP norm of a function on RD is defined as the integral over RD of my function to the pth power, and then normalized by taking 1 over the pth power on the outside. Okay. So, and when I say that m is a bounded operator, what I mean is that there exists some constant, positive, and this will depend on p and d, such that I have the following inequality. For every function that has a finite LP norm. Okay. So that's what this means. Great. And this weak type 1,1 norm is sort of a weak version of this LP inequality. Great. So this maximal function, like I said, underlies a lot of harmonic analysis, but also has very important connections elsewhere. For instance, it underlies the Birkhoff pointwise ergodic theorem. So what is this? If I take some measure preserving operator acting on a probability space, so measure preserving just means if I take a set, say E, and I look at its inverse image, the measure of that is equal to the measure of E, the inverse image under my measure preserving operator T. Then if you look at the time average, which is this quantity here on the left-hand side, okay, why is it called a time average? The sort of picture is, I start with a little particle inside some space, and there's some dynamics acting on the space. This is X, that push it to T of X, and then it pushes it to T squared of X, and T cubed of X, and so on. And as your averages get longer, you're sampling more and more points from your space, assuming that you're ergodic, meaning basically that means you're not trapped in some subspace. And as you sample more and more of the space, you're actually coming to the expectation of that function over the space. Okay, and that's the spatial average on the right. And that means, and the thing is, you're converging for almost every point inside your space, which is a very powerful theorem. Right? Sort of in the opposite direction of that, where you're considering a longer and longer orbit in the Birkhoff theorem, if you consider something shorter and shorter, you get the Lebesgue differentiation theorem. And again, that's the opposite. So it's saying that at almost every point, in Euclidean space, if I take some nice function, meaning it lies in LP, for some P, and I look at the averages of that function in smaller and smaller balls, then it converges to the value of the function at that point. Okay. This is a sort of a trivial theorem when your function is smooth, right? It's because the integrating is a continuous operation. But if your function's rough, lying in some LP, you don't get it at every point. You only get it at almost every point. And the reason you get this, both of these theorems, is because the Hardy-Little maximal function is bounded on LP for P greater than 1 and type 1, 1. Great. Beautiful stuff. Birkhoff's theorem was from like the mid 1930s, and the Lebesgue's theorem, I think, was even before that, like 1915-ish, maybe, I forget. But something much newer is Bourgain's pointwise convergence of square time averages. So Furstenberg posed a problem in the 80s, and asking if you look at square time averages, where I replace t to the n by t to the n squared, so I look at the first time, the fourth time, the ninth time, and so on, and I have these big growing gaps between my samples, you still get convergence of those time averages to your space average. And surprisingly, you actually do. Bourgain was able to show this in the 80s under a similar assumption. So if T is a measure preserving operator acting on a probability space, which you need just to make sense of the dynamics, and your function is an LP for P greater than 1, but not equal to 1, you get that these square time averages converge to the spatial average. Okay. And underlying this is some maximal function. That maximal function is, again, is similar to the Hardy-Little one. It's if I take a function f on z, to say complex numbers, and I look at the averages I look at these averages, okay? Oh, sorry. So I define this as a n f of m. Then there's some maximal function here, which is just defined as before, so I take the supreme over all n. This maximal function is bounded on LP for LP greater than 1. Okay. In general, there's a principle that says that you can't have this pointwise convergence if you don't have the boundedness of a maximal function. All right. So let's get to another modern incarnation of this. If you take some continuous function again, some nice function, and you don't average over the whole ball, but just over the boundary of the ball, okay? And so you average over a sphere, you get a spherical maximal function. This is more singular than a ball maximal function because as I increase the radius, right, the previous sphere doesn't see the next sphere doesn't see the previous sphere. It's decoupled from it. Whereas if I took a ball, then they overlap. And so you still retain partial information as you expand your ball, but you don't retain partial information as you expand the spherical maximal function. Or at least you would think you don't, but it turns out you retain enough partial information so that you can prove the following theorem. If you have spheres in 3 or more dimensions, then this spherical maximal function is bounded on LP for a certain range of P. This range of P now depends on the dimension. So the ball was all P greater than 1, and this one is actually smaller. This range is sharp. Meaning it's unbounded if P is less than or equal to D over D minus 1. Oops. Okay, and Bourgain was about 10 years later. It's 85 or 86, I forget. Was able to decrease this down to 2. And there's no hope of this happening in 1 dimension because the boundary of an interval is just 2 points, and 2 points is not enough to do anything. Yeah. But we're gonna actually prove this theorem because it's gonna be useful in proving a discrete version of it, which brings us to our second objective. If we replace those RD points with ZD points, okay, then we can define our discrete spherical averages as averaging over the lattice points, the integer points on a sphere centered at your point X, okay? And again, you form the maximal function as before. You take the biggest possible average. And it turns out that when you have sufficiently many dimensions, this maximal function is bounded for all P greater than D over D minus 2. That's different from before, which was D over D minus 1. It's a little bit worse bound, but it is sharp. Okay. So this was a landmark theorem in the field, and it still has a lot of relevance for future problems or current problems. One of the main pieces in their in Magyar-Steinwinger's proof of this bound was that they considered Fourier transforms of measures on the sphere, okay, on this discrete sphere. So if I define my discrete sphere as just the integer points that represent n, and then I take the characteristic function of that set, this is a surface measure or a discrete surface measure. Now Waring's problem said, okay, just tell me what is the volume of this sphere. So Trong asks, what's the heuristic reason for the change in the dimension? I'll get to that in the next lecture. Sorry, in the range of the LP range. Yeah, I'll get to that in a bit. Sorry. So what was I saying? Right. So if you consider this sphere and the surface measure on the sphere, okay, Waring's problem was saying how many points is on there, or in other words, what is the volume of that sphere? Okay, that was already a non-trivial question. And there's another way to phrase that is you can just ask what is the Fourier transform at 0. Okay, that's another way of asking what is the volume of this surface measure. All right, Hardy and Littlewood said it's this sort of asymptotic. And what Magyar, Stein, Wenger did was they said, well, what happens if you have a non-zero frequency, C? Okay. So what happens when I look at this for non-zero C? Well, they gave a beautiful approximation formula that generalizes the Hardy-Littlewood work. Okay. And so when you have 5 or more dimensions, and you consider such a sphere, you can up to some error term that has a good bound. You get an asymptotic formula that carries a lot of information on it. First off, this piece right here is the continuous spherical measure of radius roots square root of n, and its real Fourier transform measured near the point C. Okay, that's what this little function does here. It makes it near that point. This other function here, if you could ignore, maybe I should do it this way. If you could separate these two pieces, then this function right here in green is, it turns out, the Z mod Q spherical measure. The Fourier transform of the Z mod Q Fourier transform, of the spherical measure. Okay, so this is the real one. Whereas the green one is the Z mod Q one. And you actually get a sum over all the possible moduli. Okay, again, that's up to some error term. And this, and when you take C equal to 0, okay, it reduces to the Hardy-Littlewood asymptotic. So it's an honest generalization.
So
there's a bunch
sorry if this is a dumb question, but G here is a Gauss sum?
Yeah. So I haven't gone into what all the bits of notation are, but exactly, yeah. G here stands for Gauss. There are a bunch of things going on in this formula, right? So it's actually maybe a twisted Gauss sum might be the right term for it. So there's some nearest rational mod Q to C, and that nearest rational comes into play. It's the Gauss sum corresponding to that one, right? Much like I look at the frequencies of the spherical measure nearest to C, okay? But when you average over these Gauss sums with this character right here, it becomes a Fourier transform of a spherical measure.
And what is Psi?
C is just some nice test function. So it's going to be equal to 1 on, say, -1/8 to 1/8 in all directions. And psi is supported in, -1/4 to 1/4 in all directions.
Thanks.
So a profile of it would look like, let's So, right, so this is minus 1, oh, sorry, positive 1, 8, minus 1, 8, and then 1/4 and minus 1/4. But we'll get into what all of this actually means and how it comes about in the second part of the course. Because there is a lot to unpack here. Yeah, I mean, I haven't even gotten into how this error term is derived, nor how you prove a bound on it. Right? I say, oh, it's an error term and it has this bound, but presumably that means that this main term right here, right, is of size much bigger. And we haven't even gotten to why that would be the case. We will at some point. Great. Any more questions? Wonderful. Okay. So this approximation formula has lots of applications. For one, it's going to be used to bound our maximal function, our discrete spherical maximal function. And that discrete spherical maximal function can be used to prove L2 and pointwise ergodic theorems. And then there are also bounds for discrepancy. When you look at dilates of integer points on spheres and how they wrap around on the torus. And then there's also equidistribution, very closely related to discrepancy, and also similarity theorems and pin similarity theorems, all of which have been worked out by Alkosh-Magyar. So he's played a very important role in the development of this. And there are continuous versions of at least the L2 and pointwise ergodic theorems, which motivated Alkosh, as well as the similarity and pin similarity theorems and the equidistribution theorems. Discrepancy doesn't quite make sense. Well, okay. Equidistribution is the form it takes is the ergodic theorem. And those were worked out by Bourgain. Or no, sorry. The ergodic theorems were worked out by Jones, and the similarity theorems were worked out by Bourgain. Were there any more questions? I've got a couple more slides in case I should write something down. Okay. So the third topic is going to be on discrete restriction. And so to quickly summarize sort of what the problem is, you start with, in Waring's problem, we start with exponential sums that are of this form, right? I have my power, my degree k, and I look at this sort of exponential sum. Okay, and we use the delta method, the circle method, to tease out the representations after examining these sorts of sums. Well, it turns out that if you want to do some other problems that require more subtle information, such as Roth-type theorems, then you need some weighted estimates or discrete restriction extension estimates to come into play. And those take the shape where instead of just having I never said this and nobody stopped me, E of t is defined as e to the minus 2 pi I of t, right? So you take some sequence A, suppose it's finite if you want, or it's just lying in L2 of z, and you form the weighted exponential sum by sticking it in front of your character. Okay. Now the above exponential sum is when I take an equal to 1, right? And we're going to end up showing there's a lot of cancellation in that. It turns out that there still is a lot of cancellation if you plug in an arbitrary sequence. Okay, and the way that's captured is the following L2 to LP extension estimate. Okay. And that just says when I look at this operator and I plug in any sequence, I'm going to get some bound depending on the length of this operator, n, in terms of the original L2 norm of the sequence. Okay. Now, eta is going to be non-negative here. It could be 0 or larger. It turns out that in this case, it's always bounded by a half. But what you really want to know is the sharp value for eta. Okay. And once you do this, you can plug in, you get to play all these other games that come up in Ross theorem. For instance, if you take A to be supported on the primes or supported on smooth numbers or something, then you get a bit more information knowing this ladder bound without having to just study each one of those exponential sums with a new weight. Okay. So the nice aspect of this is you get a uniformity in the weight. There's the implicit constant here, does not depend at all on A, and it doesn't depend at all on N. So our third objective is to understand sort of the basic techniques that went into this, as well as one very new successful technique. Those techniques are, the two classical ones are the even moment method, and the circle method approach. Okay. The first one was introduced by Cook with an E and Zygmunt, I think separately, but then used later by Bourgain, and the circle method approach was introduced by Bourgain. Then the decoupling and efficient congruencing approaches were introduced by Bourgain, Demeter, Guth. Oh, hold on, I should say respectively. Bourgain, Demeter, Guth, and the efficient congruencing by Woolley. So, unless there are any questions, that's all I have to say.